Hey, welcome back to your favorite calculus class. If you remember from last time, that right there gave us the exact area, right? That limiting process. We ran the limit as n goes to infinity. In other words, as the delta x width of the rectangle goes to 0. That Riemann sum process, limiting process, gave us the exact area. Well, this is also what's called the definite integral, which is an antiderivative. So the limit is n goes to infinity of the summation of f of ci, which is our height of the rectangle, times delta x, the width of the rectangle, is equal to, and let me draw that, the area from A to B under a curve, yeah, would be the integral from A to B of f of x dx. Okay. So if you look at this first one, is saying evaluate this first example from -2 to 3. So here's our a, here's our b, there's our f of x, and there's our dx. Which, by the way, that's our delta x. That's the width of the rectangle. So using the limiting process, we could do this just like we did last time. Which, number one, what we did was we said, first let's find the width of the rectangle. Let's go b minus a over n. So delta x would be, b here is the 3. 3 minus the -2 all over n. So we got our delta x. Our width here is 5 over n. That's a terrible 5. 5 over n. There we go. And then the second thing that we did is we found the x value so that we could find the height f of ci. So the ci was a plus delta xi. So our ci here, our a here is -2. Our delta x is 5 over n times I. So our ci is -2 plus 5i over n. So we're going to use that to find our f of ci, to find the height of the rectangle, so we can throw it in to the formula right here. So number 3, our area is the limit as n goes to infinity of the summation of f of ci delta x from I being 1 to n. So we get the limit n goes to infinity f of -2, whoops, the summation, oops, sorry about that, f of ci, which our ci is -2 plus 5i over n, times our delta x, which is 5 over n. Get the limit as n goes to infinity, the summation. Well, f of x is the x, right? Let me go to the side for a minute. F of x is x. So f of -2 plus 5i over n, that just replaces the x. So I get -2 plus 5i over n. That's our f of x. -2 plus 5i over n. There's our f of x. Both goes in for x. Times delta x, which is 5 over n. And distribute that. Let me come over here. So we get the limit as n goes to infinity of -10 over n plus 25i over n squared. And so we've got the limit as n goes to infinity of, I'm going to take a 1 over n out of that first one, so I got -10 plus 1 over n squared, or I'm sorry, 25 over n squared out of that next one, I. And so I'm going to use my formulas on both of those again. So we got limit as n goes to infinity of -10 if you remember, it's constant times n. And then when I replace, I got plus 25 over n squared. And I look up the formula for I, which is n times n plus 1 over 2. Or n squared plus n all over 2. So we've got, on that, n goes to infinity. We've got negative 10n oh, I forgot, times 1 over n. That's over n there. Sorry about that. Plus 25 n squared plus 25n all over 2n squared. So negative 10, I got 25n squared over 2n squared, so that's 25 over 2. I got 25n over 2n squared, so 25 over 2n. And then I run this to infinity. That'll go to 0, 25 over a huge number, right, as n goes to infinity. And so I'm just left with the negative 10 plus 25 halves, so negative 20 halves plus 25 halves, which is 5 halves. That's our exact area under the curve. In fact, we could draw this, right? This is f of x equals x. Here's our f of x equaling x from negative 2 to 3. Actually, this goes into the negative, so we'll talk about this, but this part's actually negative. That part's positive. So that part's negative because it's under the curve, but the summation of the two gives you 5 halves on this. All right, let's do the next one. Has us change the following definite integral. So notice it gives it to us as a Riemann sum into a definite integral. So this here, the delta x, there's our dx. This here is our formula. That there is our f of x. So all I have to do is replace the ci with x. And then this is our interval from a to b. So the definite integral would be from a to b, from 0 to 4, 6x, 4 minus x, quantity squared, dx. Okay, the second one, we have also changed it into an interval as well. This one's going from a to b, so the integral from a to b. There's our dx right there, width of the interval, and here's our f of x, so it's 3 over x squared dx. All right, now we're going to make the connection, and we're going to do these problems geometrically, visually. So far we've said we can find the area under a curve for a positive function, so it's above the x-axis. We find the area under the curve using the limiting process. Well, what if we have the graph of it? So here, this is our function. F of x is negative 2x plus 4. Well, we know what that looks like. Y equals mx plus b. We have a y-intercept of 4, and the slope is negative 2 over 1, down 2, right 1, down 2, right 1. And we could continue to graph that if we wanted to. Here's our line. But it looks like we're only going from an a value of 0 to an a value of 2. So let's cut this off from 0, and there's 2. So it looks like we're doing this area. So the area under the curve, there in red, which is above the x-axis here, right, from an x value of 0 to an x value of 2. Well, hopefully you notice that this is just a triangle. So we can do this geometrically because you know the area of a triangle is 1/2 the base times the height. Well, what's the base here? It looks like it's a distance of 2. There's our base. What's our height here? It looks like it's a height of 4. So a base of 2, a height of 4, 1/2, 2 times 4, 1/2 of 8 is 4. So our area, and area is always, whatever our units are, is squared, right? Like square feet, if you're painting something, it would be area, or square inches, whatever. Let's do another one here. The square root of 9 minus x squared. And let's look at that for a minute. So here's our function, the square root of 9 minus x squared. Maybe you're not quite sure what that looks like. Let's think about that in terms of geometry again for a minute. What if I squared both sides? Now I know this does change it, but I would have y squared equals 9 minus x squared. And then I added x squared to both sides. See how we have a circle with HK is 0, 0. So it's a circle centered at HK 0, 0 with a radius, r squared equals 9, with a radius of 3. But remember, it's not the whole circle. It's actually plus or minus. It's only the top one, right? We only wanted the square root, the top of this circle, right? So it's a circle centered at 0, 0, but it's only the top part of this. It has a radius of 3. It's only because it's a positive square root of 9 minus x squared. If they would have given us y equals negative square root of 9 minus x squared, then I'd have taken the bottom part of the circle, right? It's just the top. Top of the circle, square root of 9 minus x squared, okay? So, what is the area of a circle? Area is pi r squared, but we only want half of a circle. So I'm going to throw a half in front of it. Area of half of a circle, right? 1/2 pi r squared. So this area would be 1/2 pi. Our radius here is 3 squared. So I got area 3 squared 9, 9/2 pi. There's our area, whatever units it is, squared. This is good. These next couple would be good problems to have it be a u-try problem. But here's our function, y equals x plus 1. So we got a y-intercept of 1. It's up 1, right 1, up 1, right 1, and so on. But we're only going from 0 to 2. So from 0 to 2, I'm just going to not draw the entire line here, right? So this is the area that we're finding, the area under the curve for this positive continuous function. I would probably just draw that as a rectangle on the bottom and a triangle on the top. So I have a rectangle, this whole area is a rectangle, plus the triangle. Well, a rectangle is length times width. A triangle is 1/2 base times height. So our length here is 2. Our width here is 1. And then our triangle has 1/2. The base of the triangle is also 2 right there, and its height is 2. I got 2 plus 1/2 of 4, which is 2. So this area ends up being, of both of those together, is 4 square units. And this next one we've got, here's our function, 2 minus the absolute value of x minus 1. Let me rewrite that in terms of transformations. So I'm taking here's your absolute value of x, right? There are v. I'm taking the absolute value of x, and number 1, I'm reflecting it about the x-axis. So now I'm like this, right? And number 2, I'm going to move it right 1, and I'm going to move it up 2. So right 1 up to reflection about the x-axis. And I could plot some points, of course. Let me go ahead and draw that. There's our absolute value function. You know, so again, if I plotted some points, I could plug 1 in and check it. Absolute value 0, 0, 0 plus 2 is 2. So there's the maximum, right? 1 comma 2, tip of the point there on the absolute value. Anyways, I could plot some other points if I wanted to. Now we're only going from -1, -1, right here, to 3. So just there to there. Okay, so it looks like I have another triangle here. Just doing that part and that triangle. So number 2, area of the triangle, 1/2 base times height. Looks like our base here is 4. Looks like our height here is 2. So I have 1/2 base of 4, height of 2. So it looks like I have a half of 8. Another 4 square units for our area on this problem. Now, assuming f and g are both integrable, then here's some properties. Number 1, the area from A to A. So the area from A to A, let me give you a picture of that. Like, let's say this is our function from A to A. Well, it's going nowhere, so my width is 0. So what's the area? 0, right? From A to B, you can also flip that around and put a negative in front. So negative from B to A. That's one of your other properties. The third one, if you're going from A to B, finding this area under the curve, you could split it up. You could go from A to C first, and then go from C to B. You go from A to C, add it up, and then you could go from C to B, add it up, right? You can take that constant there and put it in front again, just like we did when we were doing it with the Riemann sums. And finally, if you got a plus or a minus between them, you can split them up with the definite integral as well. So those are all properties that we'll use. So let's go ahead and use those properties here. This first one, I've got the integral from 2 to 2, right? Notice it's not going anywhere, so the width of the rectangle is 0. So this is just going to automatically be 0. Next one, I'm going 2 to 4 of 15. Well, I can rewrite that with the 15 out front, 2 to 4 of dx, right? And then I look up here and I'm like, okay, this is given to me. 2 to 4 dx, maybe I should have done it in red, is 2. So this is 2. So this ends up being 15 times the integral from 2 to 4 of 1 dx is just 2. If you want to put a 1 in there, you put a 1 in there. It's the same thing. Okay? So it's 15, and they're telling us that that value is 2. So this just ends up being 30. The next one, we've got 2 to 4 of x cubed. So I can split this up. I can write that as 2 to 4 x cubed dx, which we have a, they're telling us how much that's worth up there, plus integral of 4 dx from 2 to 4. Now remember, we can put that 4 out front. So I'm going to put that 4 out front. Let me do it in blue right there. And then I look up here and I say, okay, this one is 60. So I've got 60 plus 4, and then this one, 2 to 4 dx is 2. So it looks like I got 60 plus 8. We got 68. Next one we've got, I'm going to go ahead and distribute this through. I've got 2x minus x cubed from 4 to 2. Now I don't want to go from 4 to 2, I want to go from 2 to 4. So if I put a negative out front and switch it, instead of 4 to 2, I go 2 to 4. As long as I put a negative out front, I can switch it from 2 to 4. Okay. Now what I can do is I can split this up. So the negative does apply to both of those. And so it's minus, and notice I have a minus x cubed on this. So I can take this negative out front, which will make that positive. So I've got negative 2 to 4, and I'm also going to take this 2 out front and leave the x right there. And then a negative times a negative is a positive x cubed 2 to 4. So I've got negative 2, and then I look this up, 2 to 4 x dx up here is 6. That's 6. So times 6 plus, then I look up the 2 to 4 x cubed, and that tells us that was 60. So I got negative 12 plus 60. Looks like we end up with 48 for this one. This would be a great you try problem. I would go ahead and pause the video and try all these first. Hopefully you notice this first one. I got 3 to 3 of whatever g of x is. Either way, it's from 3 to 3, so we know that's going to be 0. The second one, I would go ahead and put that 3 out front. Now it's 6 to 1. I don't want 6 to 1. So I want it 1 to 6. So I got to put a negative out front. I already have the 3, and then I can switch it from 1 to 6. So I have negative 3, 1 to 6. Now notice the 1 to 6 f of x dx. See how that's equal to 5? So this is just negative 3 times 5. So we've got negative 15 on that one. The next one is 3 to 6. 3 to 6. Now the problem is up top of f of x. This one's not useful because that's g of x, right? That's not useful. But we have 1 to 3, and then we got the entire 1 to 6. So if you're thinking about this, remember if you're finding the area, if you go from 1 to 6, it's the same as from 1 to 3 plus 3 to 6. Okay? So that's what I would do on this one, is I would make the note, hey, if I go from 1 to 3 and then 3 to 6, that's the same as 1 to 6. Right? And I have 1 to 3. From 1 to 3 is negative 2. I don't have 3 to 6. This is my unknown here. I do have 1 to 6. That looks like it's 5. Okay, so I'm looking for this one, right? I have the other two. I have the 1 to 3 part, and I have the whole thing part. So how do I solve the 3 to 6 part? Well, I just add 2 to both sides here. And so 3 to 6 area would be 7. Okay. This one down here, I've got 6 to 1 f of x minus g of x. So I got 6 to 1 f of x minus 6 to 1 g of x. Now I don't want 6 to 1. I want that to be 1 to 6. So I'm going to put a negative out front, make that a 1 to 6, because I know what 1 to 6 is. And then minus, and then put another negative out front, and change this to 1 to 6 g of x. So I've got negative, and then I look up the 1 to 6. F of x was 5. That was 5. And then plus, and then 1 to 6, g of x is 7. So I got negative 5 plus 7, which ends up being 2 on that one. And finally, let's look at our last one here. I've got 1 to 6, negative 2, f of x, plus 1 to 6, g of x, dx. So I've got negative 2, bless you, 1 to 6, f of x is just a 5, they tell us in the instructions. And then 1 to 6, g of x is a 7. So I got negative 10 plus 7, I get a negative 3 on that one. Well, thanks so much for watching. Definite integral introduction. We'll see you next time.